Okay, so this last question that we'll do for logarithms in the official, I guess, lessons playlist. This is an applications question, and this is actually a question that I took from the workbook. So this is an applications question. It's technically not chapter 5 lesson 4. It's really chapter 5 lesson 5, and in the workbook it's on page 237 and it's number 12. But I think it's a really good applications question to try because it's really not like the other applications questions that we tried for chapter 5 lesson 1. A lot of the applications questions in Chapter 5, Lesson 5 are pretty similar to Chapter 5, Lesson 1. It's just that they're able to do similar questions that might need applications of logarithms in them as well. So you'll end up doing, for Chapter 5, Lesson 5, you'll end up doing a lot of questions that involve this formula. This is really a formula that you could use for half-life, for any kind of exponential decay or any kind of exponential growth, as long as you define your terms properly. So a lot of the applications problems in Chapter 5, Lesson 5, you can use this formula. It's just that there's the additional skill that you would have of using logarithms, so you'd be able to solve more questions in Chapter 5, Lesson 5 than you would be able to in Chapter 5, Lesson 1. Anyways, give those applications questions a try if you have time only, but I won't assign them. But I did want to pluck out this one question in particular, number 12. It is really a pure math question. Very often when we are dealing with primes, they will be some sort of pure math question, unless you're dealing with the applications that involve primes, like, for example, cryptography or something. Let's try this question. It says Mersenne primes can be written using this formula, 2 to the p minus 1, where p itself is also prime. So this whole number itself will evaluate to a prime number if it's a Mersenne prime. And the exponent that you raise base 2 to is also prime, actually. So this is kind of a really fun, interesting, strange formula to produce primes. Apparently there are only 49 of these that are known. You can think of the smallest Mersenne prime, which if the condition is that p is also must be prime, then you can think of 2 to the 2 minus 1. So 2 is prime, and when we evaluate this, we also get a prime number of 3. You can think of also 2 to the 3 minus 1. 3 is prime, and when we evaluate this whole thing, we're going to get 8 minus 1, which is 7, which is also prime. So that's how they work. We do see that this doesn't work for necessarily any prime, but any prime input for the exponent. But if you do plug in the next possible prime exponent of 2 to the 5, you'll get 32 minus 1, which is 31, which is also prime. So this is kind of a neat formula to develop primes, or to look for it, especially to look for very large primes. It's pretty cool. So here's the question. The largest known prime, by the way, we're never going to find the largest prime. There are an infinite number of primes, but the largest known prime is 2 to the power of, what is this, 74,207,281. That's going to be an enormous number, minus 1. So that's when you evaluate this whole thing, this will evaluate to a prime number. Now, evaluating this will be hard. You can try typing this in your calculator, but you'll get an overflow error. It might just say error or something, but it won't be able to give you the answer because there's way too many digits. So the problem here is that we can't really figure out what this is using a calculator, but we can using the skills that we have, we can figure out something. One thing we can figure out is exactly how many digits are in this prime. And to figure out how many digits are in this prime, one thing we'll need to be able to do is to write this in terms of base 10. If we can write this in terms of base 10, then we're going to know how many digits exist, right? So if we have something like 10 to the 1, this gives us 10, which is 2 digits long. If we have 10 to the 2, we get 100, which is 1, 2, 3 digits long. If we have 10 to the 3, we get 1,000, which is 1, 2, 3, 4 digits long. So if we can write this in terms of a power of 10, let's say we can write it as 10 to the power k or something, then we know that whatever this evaluates to, it'll be k plus 1 digits long. So if we can write this in terms of a power of 10, then that will give us our answer. So let's do that. Let's try to write this in terms of a power of 10. So again, this is more of an abstract sort of pure math question. So our goal is to write 2 to the power of 74,207,281 minus 1. We want to at least write this in terms of base 10. And we can do that. So we know that 2 is equal to 10 to the something, right? We definitely know that. 2 is equal to 10 to some power. There is some exponent that we could place on base 10 in order to evaluate this expression to 2. So what would that number be? Well, if we write this in exponential form, we say log base 10 of 2 is equal to x. So this represents the exponent that we would apply to base 10 to get 2. So we can say that 2 to the power of log base 10 of 2 is really just 2. Okay, so using that information, I'm going to rewrite this statement here. We have 2 to the power of 74,207,281 minus 1. So we have 2 to that power. What is 2? 2 is really just 10 to the power of log base 10 of 2. And I'm not going to write base 10 because I can simply write that as the common logarithm. So I will take out the base 10. The base 10 is implied. So this is really the key trick. And then everything else is just evaluating it at this point. So, or simplifying. So for our next statement, we can really just apply the exponent property. We have an exponent on the inside of brackets, an exponent on the outside of brackets. Let's multiply those two exponents. So this is just going to be 10 to the power of log 2 times 74,207,281 minus 1. And let's continue. So this is really just going to be 10 to the, what is the exponent that we are actually going to be placing on base 10 here? Well, your calculator will be able to tell you. So if you type in your calculator, if you type in log of 2 times 74 million, so on, then you'll actually get 22338617.48 minus 1. So this is 10 to the power of 22,338,617.48. What does this tell us? Well, this tells us that there are going to be, therefore, there are 22,338,617 plus 1, right, k plus 1 digits in that prime number, in that prime. So So that is a lot, right? That is 22 million digits. That would take a very, very long time to write out. You could probably calculate some sort of estimation as to how long it would take to write out. It would definitely take days and days and days to simply write out the size of this number in some sort of typical decimal expansion. So this is a huge number. It has 22,338,618 digits in that prime number. So that's a very, very large prime number. But believe it or not, there are primes that are significantly, incredibly, way, way, way larger than this prime. This is just the largest prime that we know. So there you go. A very pure math question, a very abstract, pure math question. But it's fun to try, especially because we get to apply this sort of new change of base rule where we originally had base 2, but we knew that to figure out how many digits exist in this enormous number that our calculators can't even display, we would have to rewrite this base 2 in terms of base 10, because if we can rewrite it in base 10, then we will know how many digits we have in that number. So we perform this trick. What is base 2 in terms of base 10? Well, base 2 is simply 10 to the power of log 2. There you go. So that's a nice little kind of change of base rule applied to sort of an exponential equation. So and this is a rule that's used a lot in math as well, especially with respect to base e. So very often, especially in calculus, you'll find that it's useful to write 2 as e to some power, base e to some power. Remember, e is just some number 2.71 something 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 something. It's just this irrational number. But very, very often it's useful to write, if we have 2 to some power x, then you can write that as e to the power of some constant times x. Right, and particularly what that constant will be, and you can try to play around with this. That constant is really just going to be ln of 2, or log base 2. Log base e of 2. Base e of 2. If you wanted to write e, if you wanted to change something like 7 to some power to base e of some power, you would need this sort of proportionality constant k, and in this case, k would just be ln of 7. And eventually you find this sort of nice relationship between changing some arbitrary base to base e, where the proportionality constant is really just ln of that original base. And that's very, very, very helpful for calculus, especially when you eventually start taking derivatives. But that is beyond the scope of this course. I really just wanted to show you this particular application problem in terms of prime numbers. So try some of the applications problems if you can. Try some of the review problems on page 238 if you can. But otherwise, what we'll end up doing is we'll end up moving on to trigonometry, because we simply don't have enough time in this online version of the course to stick with more logarithms questions. So there you go. That's our last applied. That's our last logarithms question, an applied question that is hopefully at least a little bit interesting. There you go.